Thank you. So I'll be I'll be talking about Astra, which is our new HPC system based on ARM64. And then I'll introduce a network. I'll kind of give you guys an overview. I'll explain some of the research that we're trying to do and some of the issues that we're running into and what we're expecting to work our way through. I'll give you some results, and then I'll bring up references that we've got, and then I'll take questions after that. So Astra is our new ARM64 HPC system. I'm one of the administrators for that system, and it's a collaborative effort. HPE, Red Hat, Mellanox, and ARM and Cavium. We're all working on it together. We paid the bill, but we're all working as a team on that project. So Astra's got HPE's Apollo 70 nodes on there. We've got 3 leaf switches on each rack. And then each rack contains 72 nodes, and then they're distributed out with a cooling system between 3 racks. We've got 2,592 nodes, and each rack has 144 processors in there. So a little bit about the Apollo 70 node. You'll see there's 2 sockets in there. There's a front socket and a rear socket. And then we have 1 EDR NIC, Mellanox, and then we have 64 gigabytes of DDR RAM, high performance, high bandwidth memory. That I'll bring up a little bit later on. One issue that we're trying to overcome with the hardware collectives that we're talking about on this talk is the fact that the number of cores is going up faster than the amount of memory that's available to them. So you have less memory available for short messages, and also for, it'll take a little more time to process things because of the, if you do a 0 copy, it takes, the CPU has to process it and stuff like that. And so we're trying to move to alleviating some of those issues by processing in the NIC. So on the Astra INFINIBAND network, we have 2 sockets, and you saw we had 1 EDR HCA. So implemented inside that Apollo 70, and this was kind of a joint effort with Mellanox leading the effort, and then Red Hat providing some of the infrastructure. We have socket, and then HPE, of course, providing the motherboards. We have something called socket direct, and each socket gets a certain number of lanes to the EDR HCA, and so that you're not having to move information through one socket to the other before it hits the HCA. And before we implemented that, we were kind of in development. We found out we were limited. I'm trying to remember exact numbers. It seemed like it was 60 gigabits per second as far as the memory bandwidth from each socket. As soon as we implemented it, we were up to 96, 97 gigabits per second, which is theoretical is 100 gigabits per second. So we were really impressed with that. And then each, in our talk here, we're going to be talking about hardware collectives. I'm going to bring up, tie all this together, but we have Mellanox Sharp, they're hardware collectives. Sharp stands for Scalable Hierarchical Aggregation and Reduction Protocol, and I'll tie all this together in, later in the slides here, and we will see how it all works. So we implemented Sharp with OpenMPI. I kind of want to make sure it's reproducible by people if they have any questions. But we set up our configuration for OpenMPI builds to do hardware collectives, and we pointed it at the default Mellanox Sharp collective folder, and then also we were using a UCX to implement it, and so there was 2 simple configuration commands to do that. I'll explain how that's all fits together here. So we have OpenMPI, and then we use UCX. There's 2 pieces to that. There's a UCS service and UCS transport. So UCS service allows OpenMPI to be able to talk to the lower levels. It looks kind of like the commands for UCS kind of look like MPI commands, so they kind of meld together a little bit. And then transport looks like verbs, and then UCS can call the transports. And then down at the bottom, what we're talking about here is a Sharp collectives tree. And so using all these commands above, we get down to we're going to be able to call the collectives. So implementing again, Sharp, when you implement Sharp, it needs to go on the Sharp aggregation manager, which is the whole command structure for Sharp. It needs to go on the on the subnet manager node. And what you do is you say, hey, I've got Sharp, I want to enable it, and then you give it a little information. You'll see up here I had Sharp enabled 2, and 2 is one of their commands, saying, hey, I've got it available. And then you'll see I told it I wanted I have a fat tree network, and it was an up-down fat tree. And so it lays out like this. And the switches actually on hardware collectives do the actual computations, and I'll show you that here in a little bit. One other point I wanted to make is Sharp on our network was a fat tree, and that's default. So I really didn't need to set up any extra commands on the configuration for the aggregation manager. But it would be, if you wanted to do something like a collective with like a Dragonfly network or something, that's available as well. Key part, so we are doing the actual computation inside the switches. And if you look real close here, I don't know if it's readable, but you'll see a maximum all reduce size. I was doing all reduces on my research and demonstration here. The maximum size I can put in there with bytes is 4096. Sandia, I was talking to a few of the guys that do our work on tweaking out our different software that we develop in-house. And they say most of the MPI traffic that we do is 64 bytes. So I've got between 1 and 4096 available for all reduce. And then our work that we do at Sandia is a lot of it's 64 bytes, so it fits right in there. And then also you'll see I've told the OpenMPI that I'm using what the port is that I'm using to enable the collectives to work, and then I have outstanding messages. I can do 256 messages, and I'll show you how that works out a little bit later on too. And then you can set up your logging, and then you can with Sharp. Every time you run Sharp, it'll probe to see what's available. And in our case, we had available barrier and all reduce. And I was doing work with all reduces here. So what the results look like, so this is kind of interesting. So this is with Sharp running and without it running. And you'll notice two things. This is consistent. First of all, we have a big improvement. This is, of course, time to execute the benchmarks. We were running the Intel MPI benchmark, and in this case, we're doing 2 processes, really 2 nodes and 1 process per node. And you'll see right away that when we're running without Sharp at this small amount of data, you'll see you'll see things like effects of the CPU processing. You'll see things like the MPI changing its operation. So for instance, at 1,000 bytes, roughly, we've got kind of a peak here, and it's consistently showing up on the next several different demonstrations. Whereas on the stuff that's executed by Sharp, you see it's pretty smooth. It's a pretty smooth curve. At 4,086 bytes, I told you that was our limit. Everything after that is executed inside the, as if it was a normal MPI operation. But anything down here on an all redos is executed by the hardware collective. I bumped it up to 1,024 nodes, 1 process per node. And again, we see our peak we see the effects of MPI and our network, and maybe the CPU operations and stuff like that. We still have that peak at 1,000 bytes roughly, but again, the hardware collectives are, it's a nice smooth curve, and then they meet, of course, at 4,096. Everything after 4,096 is pretty much being run the same way as any other operation. And then I bumped it up to 2,048 byte nodes and 1 process per node. And then you'll see we actually had 2 peaks, but again, the hardware collectives were a nice smooth curve, and things are running a lot faster down here. And then, of course, at 4,096, they meet again. So I said, well, okay, now we have done 1 process per node, and that really kind of pushes out that makes Sharp look really good. Well, how does it look when I bump it up to 56 processes per node? Because remember, I have 2 sockets. I have 28 cores per socket. So I said, well, let's go out and max it out and see what happens. There is a difference. It's harder to see on this, but there was a roughly 3 to 5% improvement on the hardware collectives, even with all that contention for the NIC from all those cores trying to reach it and say do and all redos. And then, of course, at 4,096 bytes, it merges together again. Got our references here. Some guys are doing research at Sandia, some of the guys at Mellanox. Anybody have any questions? I kind of went through that fast, but go ahead.
Questions. So, is the EDR-HCA a dual port or like a single port?
It's a single port, but again, we're using socket direct. So we've got access to some of the lanes from one socket, half of them, and then the other socket gets half the other lanes. So. Mm-hmm.
One other comment. The peak at 1,000 bytes without Sharp, that's probably because the version of OpenMPI you were using was not using the best possible algorithm for all redos. So
Mm-hmm.
trends kind of show that. So if you do the correct tuning, I'm pretty sure that will kind of flatten out.
Yeah, I was gonna do some more work with that over the weekend. We had other issues pop up, so I couldn't really get there. Another thing we were also looking at with Cavium was we were gonna do some perf testing of the processor too, and see if that was having some effects as well. So could be a little bit of, and it could be a little bit of other things too. But we're going to hopefully get all that done here in the next few weeks.
In the first slide you showed, one process per node, and you showed some pretty good benefit, you know, at this smaller size. And on the last slide, you showed when you did a lot of processes per node, it really flattened out. You didn't see the hardware collected.
Well, yeah, and I think I was expecting that kind of. There was still an improvement, but there's a lot of cores trying to reach the network.
Right. So the other question then would be, at the smaller number of nodes, you did this with the big size of nodes. If you did a smaller set of nodes but a lot of processes per node, would you also see it flatten out like this?
I think so.
So if you've got a lot of cores, then the offloaded collectives aren't providing you much benefit.
Yeah, they still provide you benefit though.
But not a lot. Not as much.
Yeah.
Were you using like multi-level algorithms? As in, there was a leader on a node and that was responsible for all the intra-node operations and was also responsible for the inter-node operations. So what kind of algorithms were being used here? Because if all processes were trying to use sharp, then that's probably going to cause some issues with the sharp daemon, and probably sharp might not be used. Explain that.
Okay, so I was just writing benchmarks on this one. We are going to do some test. I think your question maybe it goes along with what we were actually testing. So we are planning on doing other runs with like internal Sandia software and things like that, and benchmarking it that way too. But as far as what we were doing all reduces. So we're expecting to see some benefit there. Yeah. That could be too. Like I said, we pretty much just implemented it, and we're still learning with it. So there could be that issue as well. There could be a shared memory issue. There could be, like I said, I think some of it's contention to because every time you do a core to request an all reduce, there's a daemon on there, and it says, oh, I need to go out to the switch and say, hey, I'm doing an all reduce. So there's a lot of people trying to reach that switch to do that. Yeah. One thing to check. One thing I will say too is what we're hoping to do, there's benefits with computational performance, and then also because the switches are doing some of the computations and they're not having to send traffic back and forth between the nodes, we're expecting I/O performance improvements as well too. So we've got Luster on the system, and I'm leading an effort to do some work with BGFS to try it out too. But I'm going to hopefully see some benefits there as well.
So you did the switch to 1,000 nodes chart. So is it correct that when you increase number of nodes,
Yeah. So so this is actually plotted data from that run, but we saw a definite improvement as far as the computational performance. We saw basically a 50% improvement.
I mean, when we increase scale, because maybe I'm missing something with log scale, but it's around 10 microseconds. When we increase the scale, it looks like it goes lower.
Next slide after.
Yeah, if you could have 2,000 nodes, it's got better. Just trying to figure out, is it something like different algorithm was used before and now we switch to more optimal one, or it's the same algorithm
It's the same.
in both cases?
Yeah.
You mentioned you're using Lustre and you plan to probably do some testing with BGFS.
Mm-hmm.
Do you see the difference? Are you expecting to see different results with BGFS versus Lustre?
Don't know yet. We're going to check that out and see.
Performance difference might be some routing related stuff going on. You probably didn't enable adaptive routing, correct? Or do you have adaptive routing running?
We don't have adaptive routing running on there yet. That's another thing that we're going to experiment with.
And one comment, if you run more benchmarks, maybe enable some intermediate message sizes because you're probably running just power of 2, the default IMP configuration. So some issues might not show up there. So you might want to go with the message length input file and then add some more message like bytes in between.
Sure.
Not like power of 2.
All right. Well, thank you.